Well, thanks a lot, Jim and Steve. Really appreciate it being here. Now for the boring part of the conference, I'm going to talk about measurement. Now, measurement's actually a lot more interesting. Yeah, you know, the great part about life is I don't have to wait for you guys to laugh. I just keep moving forward. On that note, I'll tell you a little story about what I did as a graduate student. When I was a graduate student, my professor, Mukul Majumdar, decided to ask me to give a talk that he had. He had a paper by himself and Leo Hurwitz. And so he had a crick in his neck, couldn't go to Stanford and give the talk. So he invited me to give the talk. Now, I couldn't think of a reason to give the talk for my advisor because it was just too strange. So I was walking to the talk with Yitzhak Zilka at the time, who was a friend from Cornell. And I cracked a couple of things and spoke a little bit like an Indian because, well, I'm married to an Indian, and my brother has spent a lot of time in India, and my advisor was from India. And so he said, "Oh, you do that so well. Why don't you give the talk like that?" And I said, one of those snap judgments, yeah, why not? And so there I am at Stanford in this big hall full of people, Buzz Brock, you know, Michael Rothschild, bunch of people hanging around. And I start to talk. The purpose of this talk is to bring together, and just like you guys, dead silence. And I'm giving the talk in this accent. Another few seconds, I'm dying. I can see my career going past me, right? Until finally Buzz Brock starts screaming out in gales of laughter, and Mike Rothschild follows, and my career was saved. So it's not something I advise you guys to do, especially if it's your advisor. I never told my advisor. I did tell his cousin, and my advisor kept giving me strange looks for many years thereafter. All right, so the boring part of measurement of this conference. Not really boring, though. You see, measurement is really policy. It's what you choose to measure, okay? I mean, what you choose to measure influences what you get. It's really the fundamental aspect of what we do, both on the empirical and the theoretical side, I would say. Now, the measurement that I'm talking about is more aggregation, and looking at what it is you want to measure, what properties should that measurement device have, and what don't you want to measure, which is really 90% of the issue. There's so much data out there, you can measure anything. But it's what you don't want to measure that you incorporate into axioms that say, I want my measure to be invariant to this kind of thing. I don't want to measure it. It's invariant if this change occurs. So very recently, I've been involved in a lot of policy discussions where it comes down to a particular axiom, where the axiom is incorporating what the policymakers want in their measurement device, which then will be used to allocate tons of money for the country. So it's fascinating that axioms, something absurd and far away from policy, might be linked to it. Okay, so what I want you to get out of this is a little bit of fun stuff, such as tools to do research if you want. Also a little bit of robustness discussion. If you're writing a paper and a referee says to you, oh, you didn't check for this, that, or the other, you should know this, that, and the other, and I'm going to teach a little bit of that to you today. Also, I have a bit of new technology. In fact, the second part of the lecture is a keynote address I just gave at the bank last week, World Bank, in their second equity conference. And I'm trying to change the way they look at inequality, how it's measured, and therefore what they're going to do about it. The first part, however, is just basic theory. I assume that you know this already because you've read through the discussion from what I had put online. Therefore, I'm going to blast through it, reminiscent of Professor Heckman's discussion yesterday, except in theory. So that should be quite interesting, no? All right. How do we represent an income distribution? Well, there's a ton of ways. The way I like to think about it first is actually Penn's parade or the quantile function. We'll talk about the CDF and also vectors representing distributions. But my favorite description, and the thing that I always give in class, is the Penn's parade, which has a bunch of people walking across the stage in 1 hour, and the people are their incomes, okay? They have their own income, their height of their income, in the sense that if they're average height, it means they have the average income, and proportionally up and down that way. So Penn had this graph in his book, and you can see some people with bad draws. They had negative income. They lost money that year. But the main thing to see is how you have a whole lot of short people for a long time, right? Because the average height is up there at the line. there you get to the average in his data quite a bit further. So the median is very different than the mean in this data. And then the giants start coming in. And the really tall people, Carlos Slim is way the hell up there, who's a richest guy in Mexico, often the richest guy in the world. So this is a great depiction of it. It's just a quantile function. Brazil's quantile function for a couple of years is given here in a paper by Chico Ferreira. But that's what we're looking at as a way of depicting an income distribution. Of course, its inverse is the CDF, right? Okay, and so the CDF is the inverse of it. And what's the density function? Just take a derivative, right? Okay, where it's steep, you have a higher density function. Where it's sort of flat, you have lower. All right, an alternative description, of course, is to use a vector. And the vector that I'm going to use is not going to have probability weights. It's just going to have equal probability to make it easy to see things. And often that's how data come, although they can be weighted. So here's the list, x1 through xn. The example would be 2, 8, 4, 1. These are incomes, consumption, whatever it is that we're measuring. Could be calories. It could be any single dimension. Is there a CDF associated with this vector? Well, yeah, of course. We call it fx, and it looks like that. So you have nothing over here, and then the first person has 1, flip, 1/4. 2, it goes up to a half, et cetera, et cetera. So that's the CDF associated with that vector. Gee, I wonder what the mean is of that distribution. Can we see it just by looking at the graph? Anyone have any idea? Well, you can calculate it, and we get a calculation, we get this right here, 3.75. So I'll draw the line, 3.75. Do you notice that A is the same as B? They're the same areas. So actually the area to the left of the CDF is the mean, at least for non-negative random variables, right? So this is quite nice. You can see a picture of the mean. It's the area to the left of the CDF, or if we go back to the quantile, right? Below the quantile function. That's the mean. All right. So take a look at the CDF. There's the picture. The areas are the same thing. You can see it directly from the picture, the mean of the distribution. Now there's 3 aspects of interest when you're talking about distributions. One is the size of the distribution. The mean kind of represents that, but it can be more general. First order dominance, stochastic dominance, is telling us something about size in a very general way. Second, well, and also I should mention that welfare functions are usually defined on that to give us a notion of that that's welfare relevant. So we apply a utility function and then take the average utility, get welfare. Second is spread or inequality. And if you look at the B and A again in that light, it's kind of a proxy for how much inequality there is. How far are incomes away from that mean? But that's not the only way to measure inequality. There's tons of ways, and we'll talk about it. Third, the base. The base is to that side, the poor folks who have the lower incomes. Usually it's done with a poverty line, and then we just focus on people below the poverty line, but it's over on that side. Poverty measures are the third aspect that you can get from this distribution. It's good to be clear which one of these you're looking at in the distributional analysis that you're trying to get to. Okay? So the size of the distribution, how far to the right, can be represented by median, the mean. There are lots of other possibilities, lots of ways to aggregate those incomes, and we'll talk a little bit about that in the second lecture. Spread of the distribution, how far apart is the distribution? Variance can be used, but variance has some strange properties. You double all incomes, you quadruple the measure. Okay, so you use some other kind of an index, divide by the mean or take logs, and you get the 2 measures there. Standard deviation or variance of logs. Other intuitive measures include the Gini coefficient, which has lots of different interpretations. My favorite is it's kind of like if you took 2 incomes at random with replacement, it's proportional to the expected difference between the 2. That's cool. It's also related to that Lorenz curve stuff, but I'll tell you about that later. Normative measures have some welfare impact, and that welfare depends on an explicit assumption of a welfare function, right? So Atkinson's measures are built up from welfare to create a measure of inequality as loss of welfare from inequality. The Gini can be seen that way too. Decomposable measures, tiles measures, generalized to the generalized entropy measures, Have you ever seen the generalized entropy measures, by the way? They're horrific, aren't they? How do you understand them? What do they mean? I'll show you the way to understand them. It's trivial. You just have to see two little things and you'll understand the generalized entropy, not the formula of the summations and so on. Of course, there's a ton of other options, and my point of the second lecture is to give you an idea of the unifying theme of all inequality measures. Both inequality measures on individuals, population I mean, or group inequality, like we talked about yesterday. They're all the same thing. It's just a different way of implementing it. Finally, I should mention a bit about poverty, because that's really where a lot of my work has been recently. Traditional measure is the head count ratio. You know, the head count ratio is just, if you have the poverty line here and here's your CDF, boop, it's where it hits. Percentage of people with that income or below. Suppose you didn't know the poverty line. First order dominance. Oh, that's interesting. First order dominance is related to head count ratio, unambiguously being higher or lower. It's a paper in Econometrica with Tony Shorrocks I did in '88. There are many other possibilities besides the depth measure, the poverty gap. Sen's measure is based on Gini. Decomposable measures, the FGT has been used very extensively. FGT means Foster, Greer, Thorbecke. And we'll talk about a few of those, but we won't get into poverty so much in this lecture. I will return when I start talking about multidimensional stuff in the third part. Okay, income distribution, why should we care? Great question. Has anyone come to a conclusion as to why we should care about spread? Right, that's part of what we should be thinking about. But also, well, why size? Who cares? What about poverty? Why should we care about poverty? These are things you should be thinking about as we go through the discussion, because it's the basis of everything. Is inequality bad? Are there some forms of inequality that are good? Is it good for growth? Is it bad for growth? What kinds of inequality are bad or good? How much inequality is bad or good? Maybe it's too much that's bad, but enough is needed to get the machinery of capitalism going. This is really a controversial discussion, and it continues to be a controversy. I have this wonderful paper by Feldstein focusing on poverty, not inequality. Well, and equality of what is also a heavy question to be asked. And it was asked by Amartya Sen in his Tanner lectures that gave rise to the whole capability approach, in essence. Here we'll talk about income or consumption or a single dimensional achievement. Later on, we'll talk a bit about capabilities and what that does to our measurement, how we have to revise and create new measures to deal with the sort of basic data that capabilities come in. They're ordinal, they're incomparable. How do you compare apples and oranges to get something that makes sense? Okay. Digression, I really don't need to go on a digression, but I will. Can economics help measuring inequality? Well, no. Right? Robin says, wait a minute, utility is something you don't add or subtract. You have your utility, you have your utility, you have yours, and you don't compare. Where does it leave us? What welfare criterion actually doesn't require you to compare utilities, except in extreme case? Pareto efficiency? Right. Pareto efficiency. Yeah, go ahead.
Can I back up a little bit on that last?
If you want to.
I guess this.
You can ask a question or comment.
Yeah, I'll ask a question.
Okay.
And basically, it seems kind of weird because in a sense, like this really takes utility function very seriously, when in fact, like, what people really care about is consumption, right? Like,
Why?
in the sense that, let's say,
What is consumption? Is it an aggregate that's been constructed by economists?
No, this is consumption.
Yeah, that's consumption of that. Okay.
Yeah, that's consumption of that. So like, I may get like 10 euros from this, right? France may get like 15 euros.
Wait a minute, you're saying utils. What are utils? I have no concept what utils are.
But I mean, if you're saying utility can't be added or subtracted, so whatever your concept of utility is,
Are his utilities the same as yours? Then give him your thing. Oh, there you go. Then you're happy, right? No, it's distribution, okay? And how, if you can't measure these utils one against the other, then how are we going to compare for above and say, well, I think you need to take some of yours and give to him, or I think you should take some of your drink and give. Get the point?
This is where I'm going with this concept.
Okay, please.
So there's a certain amount of like a subsistence level of food, for example, that people need in order not to die.
Poverty.
That seems to give us like a very natural baseline for making like normative welfare implications.
Also a contended number, but continue, because it's arranged for different people, different things, Sen's big approach. That where you would die is very different when where you would die. And indeed, over what time period, because time period matters. Right? And if you've had a chance to get used to the less food, then guess what? You might survive a heck of a lot better than if you all of a sudden have to go cold turkey. Continue.
But even taking duration into account, right? Like I can say, okay, this is your lifetime expectancy, this is how much food you need over the whole lifetime. So I can change the horizon and still use that as some kind of a floor on like what is on what everybody should have.
What unit are you going to measure that in?
Let's say like people.
No. What unit are you going to measure the data in? We're here to do data stuff. Data.
Calories. Or
Calories? That's a good approach. My poverty measurement paper did not use income, it used calories to measure poverty in 1984 paper in Econometrica. So I'm with you there. Okay, we're in agreement. So?
Okay. No, I mean,
what's the right cutoff, though? What's the right calorie cutoff? And in fact, what about protein? And what about the micronutrients? Multidimensional.
This is the point that I'm making. I think that sometimes like, we kind of like, raise our hands up in the air as economists and say, oh, we can't make any normative implications because people should do utility functions and that sort of stuff. And
I'm just saying that this is the standard thing that economics would say. I'm going to go back against it in just a second. Okay. Give me a break. Okay. I'm with you on it. I think we can go a lot further than what Lionel Robbins was saying. Okay. We reasonably have a sense of people's well-being as they say it. We reasonably make judgments all the time. But then if we go back one step and ask the more fundamental question, what are you able to do or be? This is the capabilities question. And then start characterizing the fact that you can move from here to there, but you can't. You don't have the ability to move from here to there. And that's a fundamentally different situation. There's inequality here. How do we deal with that? So there are ways of comparing people in more fundamental spaces than income, than other areas. Yeah.
I mean, in general, I feel like the Robbins argument comes out of a revealed preference approach to the concept of utility. But if we take the purely revealed preference approach to the concept of utility, then there's no reason to believe that utility has any normative implications whatsoever. So a Pareto improvement is not even necessarily an improvement because you can go, okay, this person's managed to increase his utility without doing anything else, but so what if it's just revealed preference and preference doesn't even mean anything in this
Well, revealed preference is proportional with what's going on underneath. That's what makes it have validity. But yes, I agree. There are theorems that have been proved, and the theorems give us the results in the interpretation we need to imbue revealed preference with its power.
Yeah, but I mean, you're robbing the whole structure of any normative implications as soon as you start trying to
Agreed.
That.
So here's the results we rely on heavily in our first or second micro class. Fundamental theorems. I wrote a thesis on fundamental theorems, for goodness sake. While raising equilibrium is efficient, Pareto efficient allocation can be sustained as a while raising equilibrium so long as you move around the initial endowment. Okay, first one, non-wastefulness. Second one, non-biased or unbiased. But this is a really weak criterion. It doesn't tell us anything. If I have everything, you have nothing, Pareto efficient. So it isn't going to tell us anything about inequality, I'm afraid. We can't really look at the contract curve and see what's a better and what's a worse point. So we have to fundamentally go beyond Pareto. There's no doubt about it. Welfare functions are a way of aggregating preferences to obtain social ranking, but the problem is, as we know from Arrow's theorem, that you get all kinds of interesting impossibilities that Sen would interpret as a paucity of information. When you have ordinal, non-comparable preferences, what can you really say? So you need interpersonal comparability. The way that economists have tended to do it is to assume a kind of ideal utilitarian welfare function, whether it makes any sense or not in the real world. We view our normative analysis in terms of this lens very often. So let's suppose you do have an individual welfare function. A utilitarian would decide that we'd average up utilities and divide by the number of people, at least the utilitarian that I'm looking at that wants to compare across different populations with different sizes, different numbers of people. So each U of I has diminishing marginal utility. That's what strict concavity means. You get a complete ordering. How does all that relate to inequality, though? In utility space, utilitarians don't care about inequality. Think about it carefully. It's a sum of utilities. It's a point Sen made that people tend to forget. Oh, we're so caring about inequality. But you're caring only about inequality in income space. The theorem at the bottom tells us that if you have identical utilities, and that's typically assumed, kind of from a veil of ignorance idea or something else, identical utilities, then if you maximized, you'd get equal levels of income. There's the link. And that's the fundamental link that gets us to a theorem by Atkinson in his brilliant 1970 paper. We'll get back to that in just a second, and much of it, that's the digression. We really digressed. I was very happy to see that. Measures and properties. Inequality measures. What is an inequality measure? It's basically a function from the set of all income distributions to the real numbers, or some other space to represent the ordering. It can be multidimensional. It can be actually mapping to a vector space ordered by vector dominance. An example of that is the Lorenz curve. 4 basic axioms for inequality measures. 3 of them are pretty well understood. The final one I'll explain. First one is symmetry. You flip around incomes, and you have no change in the inequality measure. Now, the assumption is that all differences across people have been accounted for. You've already done the equivalence scale. You've already done everything you needed to do, price differentials across regions. That whole discussion we had the other day about consumption versus income, that transformation's been done. At which point we can then say, yeah, it doesn't matter who has what. Except for part of the analysis, we're interested that one type of person might have more, one has less. Second, a replication of incomes, it just means that if you take this room full of people with your income levels and made another one across the way, cloned everyone, then the overall inequality level shouldn't be changed. That allows you to compare different sized countries or regions in a coherent fashion. If you don't have measures with this property, you start, yes, I know the income in China is big, but there's a lot of people. If you don't divide by number of people, it's a tough thing. Yes?
Yes, the question was
Sure.
property. So if you put down income, so then is that looking at the income as kind of this scalar dimension of inequality? Because it's like, say for example, if I have like 10 kids, right? Like if you switch my income to somebody with like 2 kids.
Equivalence scale. Equivalence scale accounts for how many kids are in the family.
Okay.
And accounts for other relevant aspects for the purpose at hand.
Okay.
Maybe you'll want to keep it at the family level and not count at all these other extraneous details.
So you'll kind of like bend the income distribution by some other characteristics, and then you look for that.
Absolutely, that's how it's done.
Okay.
Yep. Now, for earnings, are we really going to bend anything? Probably not. For income, for consumption, there's more to bend. Okay. Proportional change. So this gives it the kind of relativity that when you double all the incomes, you have no change in inequality. This is telling you what not to measure. We don't care about levels, we care about relative inequality. And then finally, this is an old principle from 1920, Professor Dalton at the LSE. It's the transfer principle. And it says if you take money from a rich person, give it to a poor person, inequality falls. You take money from a poor person, give it to a rich person, inequality rises. That's all this is saying. This is the essence of inequality measurement. As incomes go apart, there's more inequality. As they go together, there's less. All right, any measure satisfying these will be called a relative inequality measure. Let's just give it that name. Those 4 basic axioms. Has anyone read de Broglie development text? Any development folks? So this is the structure that he has in his text. Now Lorenz curves. How do you construct a Lorenz curve? It's straightforward, right? So here's an income distribution 861. Order the incomes lowest to highest to obtain the ordered version. The ordered version has hats here, 168. On the horizontal axis, plot P, the cumulative percentage of the population. On the vertical axis, plot Lx of P, which is the cumulative percent of income received by each cumulative percent of the population. Now the fact is that you have discrete distributions, so exactly what do you do to fill in the gap? Here's the way you do it. Find the cumulative shares of population up to each I, right? And then that's P is equal to I over N. Find the cumulative share of income up to each I for each one of the persons I, and then put the dots together. And that's how you construct the Lorenz curve for discrete case. And that's an example for this distribution. So 1/3 of the people have 1/15 of the income. 2/3 of the people cumulatively have 7/15 of the income, and of course everybody has everything. There's a plot, it's horrible. It doesn't look like a Lorenz curve, but you get my point. P here, Lx of P up there, and there you are. So at any population share, Lorenz curve gives the share of income received by the lowest P share of income recipients, often stated in percentage terms. This is a really crucial concept. Who's Lorenz? Anyone know? Okay, Max Otto Lorenz. I'll give you a hint. He's not Italian. Bingo! Wisconsin PhD. In statistics, I believe, but yeah, you might be right. Well, let's see. You sure it's economics? Well, why don't you look on the computer and find out for me, will you please? But anyway, Max Otto Lorenz was from Iowa and went to University of Wisconsin, did his thesis. This is the thesis paper. Not to be confused with Lorentz. Gasworth in '71 gave us this lovely definition, which is just, take a look at the quantile function, integrate, you get that function, that's called the generalized Lorenz curve, and divide by the mean. It's so pretty. This is what I use all the time. It's how I can prove a lot of things that people had to do a lot of work proving before. So here's the picture. There's your CDF. Flip it, and that's the quantile, the inverse of the CDF. Integrate up to, say, P bar. That's A. Plot against P bar, A over the mean, X bar I'm calling the mean in this particular slide. It's an old slide of mine. And do the same all the way up and down the distribution. That's the Lorenz curve. So you have a great pictorial representation of Lorenz curves in terms of CDFs and quantile functions. All right, so what are the characteristics of a Lorenz curve? Starts at 0, duh. Ends at 1, 1, duh. Always convex, as you can see why you're integrating something. Increasing. What's the Lorenz curve of a perfectly equal distribution? Right. What's the Lorenz curve of a perfectly unequal distribution? Well, it looks like that kind of, but there is no perfectly unequal distribution unless you have vanishingly small people, right? Because there's always someone with income. Anyway, that's a trick question. So it's this thing right here. Interesting question for you. Suppose I told you that there was an index that had the property that if you gave me an epsilon, any epsilon, it could be 1 over 3 million, I could construct distributions, 2 distributions, one of which had a Lorenz curve epsilon close to that diagonal, and another distribution epsilon close to this L. And yet that inequality measure said that this was the more equal one and that was the less equal one. Suppose I told you that there was a measure that did that. Would you use that measure? Not if you cared about Lorenz stuff, right? Oops, it's the standard deviation of logarithms. Oops, variance of logarithms. Yes, indeed. Variance of logarithms has problems at the upper end that come all the way through to the lower part of the distribution. A paper of mine in Econometrica a few years ago. Have a look at it if you're a labor economist. It's always nice to know what's going on with, measurement that you usually. One of the problems with it is that if you have a lot of inequality or a lot of action going on at the upper side, it can really distort your measure of inequality overall. Okay, so it's good to be careful of that measure. Okay, Lorenz criterion. We say that X, Lorenz dominates Y if it's above it, or at least it can be the same, but somewhere above it. So X is unambiguously less unequal than Y. Example 168, 159. You can see the graph right there, an example. All right, that's our sort of unambiguous idea of less inequality. Lorenz criterion isn't complete. You can have crossing curves, right? In which case Lorenz says nothing. Until you get to some papers I wrote later on which show you how to generalize the Lorenz criterion in particular cases. We'll talk about that later.
And why do you say nothing?
Sorry?
When you say it says nothing, is it partial ordering?
Right. I mean, if the Lorenz curves cross, then by the Lorenz criterion, which says it has to be dominant, it doesn't say anything. It's incomplete. Right? It says...
Yeah, no, when I was maybe pushing a little bit on is when I worry about the assumptions for different criteria. Everything that gives a partial ordering you would accept because it has weaker criteria associated with it.
I don't mind partial orderings. I don't mind quasi-orderings. In fact, I think it's the basis of much of what we do in economics because we have contending and conflicting goals. And partial orderings are a way of expressing that conflict. But I just wanted to say that the Lorenz curve, you know, it doesn't say anything to us, the Lorenz criterion, in this case, by definition. Of course, you can generalize it, and you can make statements. In other cases, you can use a specific measure, right? That emphasizes the part of the distribution you're interested in, but we'll talk about that in just a moment. How does the Lorenz criterion fare when you talk about those basic axioms? Guess what? It satisfies them all if it were a measure of inequality. You can see why. I mean, replication and invariance and anonymity or symmetry, I mean, you need that when you talk about the CDF. It's already incorporated in a CDF. Scale invariant, it's already incorporated by dividing by the mean. Regressive transfer, you just have to prove this, but it's true. It's the essence of the Lorenz curve. In fact, there's a great result that says that if you have two Lorenz curves over two distributions, same number of people, right? So you have two distributions, same number of people. Two Lorenz curves, one dominates the other. You can obtain one from the other by a sequence of transfers. It's an old result by Muirhead, 1912 or something. Lorenz consistency. We say that a measure is Lorenz consistent if it follows the Lorenz curve when it has something to say. So it's consistent with when the Lorenz curve says that it's equal, the two distributions are equal, it says equal. If it says more, then the inequality measure says more. And this is a criterion one might put on inequality measures. We want to make sure they go with the Lorenz criterion. So there's a theorem, very simple one, that shows that Lorenz consistency is embodied in those four axioms. You can check the four axioms and then you know that you're consistent with the Lorenz curve. If Lorenz curves don't cross, then all relative measures are going to agree. You can just use one and you're done. No robustness needed. If they do cross, then one relative measure is going to go one way, another relative measure is going to go another way, so you got to pick between the relative measures. Yep?
Why is scale invariance important? Like, say, for example, if everybody's income doubles in the United States
Yep.
from 1970 to 2000, right?
Yep. What are you looking to measure if you're not going to be looking at a scale invariant measure?
I guess, I mean, the challenge with that is I think that levels do matter. Like when you,
They do matter for measuring size, for measuring poverty, for measuring relative inequality.
okay, say for example, okay, so the tax code that we have, right? And let's say, for example, as guys get richer, they start to make more generally from
Yep.
half of those taxes, right? And so my income doubles, all of a sudden, like my investment vehicles change, right? And now I'm more in the market, right? And so I'm getting a lower marginal tax rate. So I'm getting the Romney special of like 13%, right? There are a lot of other mechanisms that can kind of like amplify like the changes in scale over time that would be missing from that measure of inequality.
So what's the alternative? Economists always look for the next best thing. I mean, if you don't think this is good, let's go to the next one. What's better? Variance?
I mean, I just think it would be nice to have a measure that could have all four properties, or you can slide it back down to just having the three, so that in some sense you don't completely like collapse.
In fact, if you go to three properties and look at size, that is a measure that is used frequently. Measures of size. Take into account not just transfer and the others, but also take into account the size and get to distribution, discount. If you have more inequality, then the total size is lower, right? That's these sorts of measures that are transfer sensitive, but they also measure size. So you can do them both. And you can also do poverty measures that are distribution sensitive, pay attention to the cutoff and so on, okay? But I agree, there are other measures that are translation invariant, that if you add the same amount of money to everyone's income, then you'd have the same level of inequality. The problem with that is recessions. Because if you take away the same amount from everyone's income, not many people are happy in saying that's the same level of inequality. So this type of measure was called leftist, which in an expansion economy is appropriate, but in a contracting economy it seems quite rightist. Okay?
Kind of like a conceptual question. So like as we
Okay.
add all of these,
I think they've all been conceptual, but keep going. Okay.
as we add all of these structures on it, in a sense, like the way that it's been presented, like these are like desirable properties.
The basic ones pretty much are.
I guess like we can take the merit of that and say like these are additional like restrictions, and in a sense like we're losing the basic freedom that we require our inequality measures to take on these various properties.
But we do that every time we do any measurement exercise. We intentionally lose degrees of freedom because we're not interested in those degrees of freedom. We're interested in this. We're not interested in that.
Making some value judgment, right?
Yeah.
How to use them.
Yeah,
So
that's-
like by defining them in a certain way, we already say that that's kind of what we care about.
That's what we care about. And we get back to the question, what we measure is what we care about.
Is that what we care about?
Maybe not. This is just a framework, the basic framework for relative inequality measurement. You can vary it as you wish. That's what's interesting about it. Once you have the tools, you can actually say, well, I don't like that. I like this other thing. And here's a measure that gives me that. It seems like you might go in circles, but you don't.
So kind of like one final question is,
Yeah.
so if somebody proposes an equality measure, they say it only,
You heard him, one final question, right? Okay. I'm holding you to it.
and somebody says, I have a measure of inequality and it only needs to satisfy one axiom. And somebody else comes with the four axioms that you put up there, right? Let's completely keep them in black boxes. As a professional, from a value judgment standpoint, like which measure of equality?
Thank goodness the market determines this. It's wonderful. And the market has usually determined measures that don't satisfy all these axioms. And in fact, I'm having to unify inequality and take into account the 90-10s that don't satisfy these axioms. To take into account the Kuznets ratios that don't satisfy them. So I'm with you. Don't worry, I'm already there moving in that direction. But I'm presenting the basic theory as given in before 2000 in the book with Amartya Sen. Okay.
I just want to, I don't want to interrupt the flow.
Please.
It is your lecture, but you made at the very beginning saying that you were interested in answering certain questions.
Yep.
You never point stated why these are the interesting axioms, what questions they really answer.
No.
I mean, suppose that I want to determine sort of the political economy, the redistribution.
Then the polarization
or
is going to be
or
better.
the degree of loss of, I mean, I don't want to use the word utilities, let's say.
No, I don't mind.
No, to some degree. I mean, we think about almost a cardinalization when we think about uncertainty.
Yep.
And so some of the
It's the same
distinctions
thing.
between sort of certain aspects, I was thinking briefly, referred to, we're going to talk about this later in the lectures, but the difference between the uncertainty component of the variability and the certainty component of the variability.
Right.
So again, are you going to talk about this or just?
You know what? I'm going to present the general framework, get into variations on it. I don't know if I'll hit that exact question, but hit me at the end and say, all right, you didn't talk about that. How would that be addressed?
But I mean, why would I care? I mean, symmetry or the anonymity principle is a very strange thing if I'm thinking about
Really?
political economy. Yeah.
I mean, well, then
So I
what is
have, I have a
it?
distribution now,
Yeah.
and I mean, you know, you're going to hear the phrase, "You're better off than you were 4 years ago." That'll be said repeatedly in the next 6 months or so. And that really represents an initial position. And so it's not the marginal distribution taking off, it's the additional distribution today, asking how did it shift over the last 4 years.
So you're looking at a mobility question in that case,
Well,
more
mobility,
than
it's sort of
an
the
inequality.
visual advantage. I don't really care. I mean, I don't know whose position you're taking. Is this kind of like a third person, Adam Smith, sort of impartial observer? Or
Well, the real question is, what are we interested in making equal?
Who cares
Right.
about these axioms? I mean, I've always wanted to ask you this question.
Please do. What is it that we care about measuring? Okay? What do we care about measuring? What do we care about being equal? Is there something that fundamentally is interesting to be made equal? This is Sen's point in his Tanner lecture, many other lectures. He said, every philosophy has a focus on equality in some space. It just depends on the space you're interested in. If you're a utilitarian, even if you don't have identical people, you're interested in equalizing marginal utilities.
So James, just follow up
Yep.
with Jim's comment.
Yep.
One of your examples, I think, is called into question, which is the relationship between economic growth, for example,
Yep.
and inequality. There, it's not obvious in any of these measures is the appropriate object in terms of what the mechanism is that would map an income distribution and growth rate. And so I think that you're on the strong ground that you work on is that there's certain philosophical reasons there need to be criteria, so these criteria are useful. But if we wanted to put in the application, let's say growth,
What's great about it, it is an empirical question. And so at the end of the day, we can have a discussion in that space to talk about it. We can also construct indices that are appropriate to the model that may or may not reflect the ones that I have here.
okay, well, I'll push you harder on that now. And it's not you, but growth economics has failed to come up with any sensible mapping from measurement of inequality to growth. In other words, there's theories that say that the distribution itself will affect growth, and they say, oh, but we're going to use the Gini coefficient. That's the sense of the failure there. And so,
Well, I'm going to show you a twist on this whole question, but it will be the second lecture. And to show you that in fact inequality measures include within each of them growth. In other words, discussion of changes in inequality.
we're not using the same term. I mean,
Yes.
if you take cross-country growth regression, people make arguments that the level of inequality in society affects its growth rate.
Yeah.
Because they aren't explicit about the mechanisms, it's not clear that the empirical proxies they use, which come from this literature, are the appropriate ones. And from the perspective of predicting differences in growth rates across countries, it's not obvious that any of the criteria which have philosophical grounding are relevant.
That's fine. I have no problem with it.
And that's how I interpret things.
In fact, for any empirical application, these measures may or may not be relevant instrumentally. But what we're saying is they may have, and hopefully do have, because they're part of the discussion that you all used, they do have certain end product interest.
Yeah, as I said, it's not a comment about what you're doing, it was more
Okay.
about the application of these in.
No problem. So the question is how we're going to use these guys, and we can use them on one side of the equation or on the other side. And it depends what you're doing, right? What you might use on each of those. But I'm presenting the universe of inequality measures to you. And the universe requires us to discern between the different actors in the game. Okay, so how do you classify these things? One way is by motivation, positive versus normative. Actually, positive is part of the discussion we're saying in a sense, but normative, does the inequality measure have within it a kind of concept of welfare underneath it that's sort of pushing the interest in inequality? Or statistical, so many measures are just basically variance-based. Or by properties that they satisfy. And of course, a lot of measures are not Lorenz consistent, so let's talk about some of them now. So the range measure, this is a fine measure of inequality. I'm just talking about range, where you have the highest income, the lowest income, put it over some one of the two or the average. Of course, this satisfies very little. In terms of the transfer principle, it ignores the big center of the distribution. 90-10 ratio, you can do this in logs as well. Of course, it ignores the distribution apart from the 2 points. It violates the transfer principle. And wait a minute, it might violate it in interesting ways too. So if you have more inequality at the lowest end, right, then it'll actually go the wrong way, among the poor. Okay, so there may be more serious problems than just the sort of vague neutrality violation in the middle, that it just doesn't pay attention in the middle. Kuznets ratio, the share of the income earned by the richest R of the distribution, R% of the distribution, over the share of income earned by the poorest, P share of the distribution. These are ratios defined by points along the Lorenz curve. So you take 2 points along the Lorenz curve and compare the size of those. Like the range, it ignores the distribution between cutoffs and violates the transfer principle. Relative mean deviation, those two areas, the A and B things we were talking about, that's what this is. You look at the absolute difference from the mean. It's not sensitive to certain transfers and violates the transfer principle. The variance, a great measure of dispersion. Of course, it goes up 4 times when incomes are doubled, so therefore, in terms of a relative measure, it's kind of a super measure, if you will. It doesn't satisfy that scale invariance. But the variance of logarithms does satisfy scale invariance. You see why, right? Here's the trick that occurs. The log converts, right? If you double all incomes, you get a log 2 floating around. And that log 2 also affects the mean the same way. And so therefore the log 2's cancel everywhere. And you have the same variance of logarithms, or standard deviation of logarithms. So it satisfies scale invariance. But of course, as I mentioned before, it can be incredibly Lorentz inconsistent, which, if it's an empirical problem, I'm not sure, but it certainly is a theoretical problem one must be careful with. More properties and measures. Here's some additional properties that are thrown out for your enjoyment. Normalization, if everyone has the same income, 0 inequality. Sounds reasonable, right? Continuity, it's a standard continuity of convergence. Yes?
Does this cases when the variance of logs is Lorentz inconsistence arise in practice, like how often?
Variance of logs, there have been a number of cases in practice. Creedy is the guy who's done that work. But the thing is, people haven't been looking for it, and also it's hidden. Because if you have 2 impacts occurring simultaneously with an impact that allows the variance of logs to reflect things correctly, but then things are going badly, it dampens that part of the evaluation. So the combination of the two, you wouldn't see it. You'd still see that it's more, but it just isn't as much inequality that's been added. Because as you add inequality among the rich, it actually lowers inequality as measured by the variance of logarithms. Combine that in with whatever was happening down here, and it could be not observed empirically directly as a reversal, but it certainly is affecting the numbers you're getting. That's what we argued in the paper. Continuity. Transfer sensitivity is a different type of property, but a very interesting one, and it's related to third-order stochastic dominance, just like the transfer principle is related to second-order stochastic dominance. It says that if you have a transfer down here at the lower end of the distribution, it has a bigger impact than at the upper end. A way of doing that is to take a regressive transfer here, a progressive transfer here, they're the same size, and the progressive transfer doesn't win. It's the one at the lower end that wins. Okay? So if you satisfy that transfer sensitivity, then what's interesting about it is you can say more than just Lorentz consistency. You can go further to comparing cases where Lorentz curves cross. You have fewer inequality measures, they agree more often, and you can make stronger statements. In particular, if the Lorentz curve of one distribution starts higher, crosses once, and that same income distribution has the same or lower coefficient of variation, then it's more equal by all these measures. Crossing still can be evaluated. And that adds another 20% of comparisons in most data sets. Subgroup consistency, this is policy relevant. People care about this in the ministries around the world. Let me give you the idea. Suppose you had a measure that you know that if inequality increased over here in the south and inequality increased over here in the north, and let's say we haven't had migration that could have caused that change. We haven't had even the means changing in each of the two regions. So it's a pure distribution effect in both regions. Inequality goes up here, up here. What would we hope would happen overall? Between group is unchanged. So it's just the aggregate within group that we're seeing change. Well, if a measure went down for the country as a whole, there might be problems in dealing with that case. Explaining to people why the measure went down here, went up here. This is the problem with the Gini coefficient. The Gini coefficient is a great measure, wonderfully intuitive, but it has this fascinating problem that when you separate populations into subgroups, it isn't consistent, the numbers in the subgroups, with the overall numbers. To the extent that even an increase here and an increase here can lower the total amount. And the reason why that happens, we'll talk about in a second. Additive decomposability, that's kind of implicit in my discussion a second ago. You have inequality, say, two groups, X and Y. The inequality within term is an average within group inequality, where the weights are Wx, Wy, on inequality of X, inequality of Y, plus a between group term. Now this between group term is built on that smooth distribution I talked about with normalization. And it means that you take all the incomes within group X and smooth them to the mean. All the incomes within Y, smooth them to the mean. So now you have only between group left, take the inequality of that. So this decomposition is actually extremely useful. It's why the tile measure came into the fore and why people have done a lot of work with the tile measures and now the generalized entropy measures. And it does imply subgroup consistency, doesn't it? Because if you have the between group holding fixed, because this depends on means and numbers of people, it's holding fixed. And the weights are holding fixed because they depend on the mean and the number of people. The within group terms, the bits of the within group in X and within group in Y, they go up, well then the overall is going up. So it satisfies, the additive decomposability gives you this relevant concept for policy analysis, the subgroup consistency. Okay, so that's, I argue that this is relevant. Sen hates subgroup consistency. And we have arguments in the book. If you looked at the discussion, he talks about it. Well, what would happen if, again, it's all actually a critique of symmetry. What would happen if I had links to people across another group? And maybe he put it this way, that if my first name, we group people by the first letter of their first name. Well, there's probably more links across groups than there are within groups. So why would we care if inequality rises within a group? Well, you care about it because it could be that same data for other reason that you have those groups. And so the inequality measure can't be any different. And so you have to simply get it for any groups. And if you're concerned about links between people, incorporate that in your measure of income a priori. Otherwise, symmetry doesn't even work. Yes?
So has anybody actually looked to see what people do care about?
Yes, they have. There's been lots of experiments that talk about, it seems that they care a lot about polarization and a lot about inequalities between groups.
Okay.
Very salient. Inequality across individuals is hard to conceptualize. And so therefore there's less caring about that.
But these experiments don't look to sort of try and distinguish preferences over, well, which index closely matches people's preferences.
They usually like test axioms and then toss out indices on the basis of axioms not acceptable. And sometimes we do have refutation of certain types of axioms. But what's interesting is that you get another data set, another group of observations, and you get different results. I haven't seen a lot of conclusive evidence from the experiments, but it's a great way to continue to kind of add to our understanding. But, yeah. Okay. So subgroup consistency, additive decomposability, pretty important axioms. Let's consider indices that actually satisfy the Lorentz consistency. Well, the squared coefficient of variation. I use squared coefficient of variation because then it becomes a member of the generalized entropy measures. But you can use coefficient of variation. You can use any transformation of this index. Essentially, it's taking the mean, the variance over the mean, the standard deviation over the mean, and squaring it. So it's straightforward. It has all the properties. It's additive decomposable. It has strange weights on its additive decomposability, right? It isn't like the variance with population share weights. Okay. But it has additive decomposability. Gini coefficient. Can you understand the Gini coefficient by looking at that stuff? These are the formula. Let me explain the first formula. It's the one I just mentioned. Take a look at this double summation and put it over the n squared. That's really the expected difference between two incomes drawn at random with replacement. That's over twice the mean. That's the Gini. The second definition. It's weird. Why would they ever have min of whatever? Okay, the min, put it over n squared, that whole double summation. That's a measure that's actually quite interesting. It's Sen's welfare measure, and we'll talk about it later. It says pick 2 incomes at random, and rather than just saying, well, I'm going to average things up, I'm going to choose the min of the 2, kind of slightly Rawlsian. Take the min of the 2 and put it in that little entry in the matrix, and then average. So then I'll have the mean minus that Sen welfare index over the mean. That's the Gini. Now we'll see that in an example here. The first definition is given an example here, where I've taken 1, 2, 3, 4. What's the differences? Well, 0 from 1 to 1. Between 2 and 1 is 1. Between 3 and 1 is 2, and so on. So that's the matrix of differences, absolute differences. I take the mean of that matrix. Okay, you can easily do that, right? Just add them up and divide by the number of entries. And I get, kind of haphazardly, 20 over 16. The mean is 10 over 4. And so you get, as a result, the Gini of 1/4. Just put the ratio of, you take the mean minus the Sen item here over the mean. So mean minus Sen, multiply that by 4, you get what? 40, 20. You know, I love it when this happens. Put it over twice the mean. Yeah, okay, you get 1/4. Continuing on, look at it in terms of this case. We have the definition 2 is, this is very strange. That shouldn't be that at all. That should be E expected minimum of the 2. Then you get 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 1, 2, 3, 3, 1, 2, 3, 4. That's the matrix of the min of the 2 drawn at random. Look at the average of that. It's 30, and there's 40 over 16. G is 40 minus 30 over 40, which is 1/4 again. So the Gini coefficient can be calculated by, very basic means. You don't have to look at this graph and try and calculate it as areas, which is impossible. And you add up squares and integrate and all that. It's a lot easier to do it the other way. But in any case, the Gini coefficient in this graph is A, right, over C, DO in the language of the old style economists, okay? So it's really A over 1/2 or 2 times A. It ain't subgroup consistent. It's all kinds of examples that I can give you, and it's not decomposable strictly. It's got a breakdown, but that breakdown has a residual. The residual depends on, with the 2 groups, how much overlap there is. Now, if I want to measure this overlap, and I consider it to be important, it may be a great measure to look at. But if that overlap is troubling and you can't explain it, then it may not be. Tile's first measure, this is the measure. I'll give you a simpler definition after a while. What does it mean? Well, it means that we're really looking at entropy, Shannon's entropy measure. You're subtracting it from its maximum level, which is log of n, the number of entries. And you get a measure of inequality, because the entropy measure is measuring equality of probability of things happening. Okay, so therefore you get inequality. So S of 1, 0, 0, 0, Shannon is 0 because you have no entropy. S of 1 over n is log n. That's the highest level. You have maximum entropy. So you're taking from the max entropy, the entropy itself of the shares of income. And that's what the Tile measure says. Does that make any intuitive sense to you? It doesn't to me either, so we'll go on. This does make, Lorentz consistency is satisfied by the Tile measure and everything else under the sun, and has very interesting weights on its decomposition, which is the share of income in each subgroup. Tile's second measure is more interesting, and this has assumed a great priority in the way people measure inequality now because it's so intuitive. It basically is based on the arithmetic mean and the geometric mean, G for geometric mean here. So that formula, don't worry about it. Look at the bottom here, log of mu over G. Mu over G is greater than 1, log of that, you get it. So this is the mean log deviation. It's got every property under the sun, and it's decomposable with population shares. So this is a great competitor for the variance of logarithms. It's actually of the same family because it also, variance logarithms, is decomposed using the same weights. This is Lorentz consistent, additively decomposable with these weights, so forth. There's the horrible family of measures. I'm putting this up to just make you say, oy. Fortunately, we don't have to depend on these formulae, because I'll give you the intuition later as to what this really means in terms of inequality. But as you can see, it's, Theil's measure is there, the Theil's second measure is there, and then you have this entire class of things with the alpha powers that don't make any sense to anyone. All of these are Lorentz consistent. The alpha has this neat interpretation as an indicator of inequality aversion. It's sensitive to transfers at different parts of the distribution. When alpha gets high, it's focusing on the high incomes. When alpha is low, it's focusing on the low incomes. Really quite neat in that sense. Just it doesn't make sense yet. It's additively decomposable with weights that may not make sense. The only two measures that have weights that make sense that add up to 1 actually are Theil's measures. Then there's normative measures. I say normative measures because they have the intuition as being inequality is the same as the loss in welfare due to this dispersion, this inequality. The core idea is that, and it was given by Dalton in 1920. He measured everything in utility space. Atkinson decided to bring it back to income space with something called the equally distributed equivalent income. So he then defined a new measure as the mean minus the EDE over the mean, very much like our Gini, which was the mean minus the sen over the mean. Okay. Sen went on to kind of go further to get more measures included into this class, including the Gini coefficient, which has the sen welfare measure behind it. This equally distributed equivalent is a real fundamental concept. So let me just spend a second explaining it. For those of you in finance, you know it already, certainty equivalent. But for those of you who aren't, let me explain it. It says, what is the level of income which, if given to everyone, would have the same level of welfare, right, overall, as the existing actual distribution? So you solve that equation, if you will, find out what E would be, all right? So picture looks like that. If you have a welfare function that's usual, okay, then A is the initial distribution. The mean is given right there at E. Okay, everything along the line has the same mean. And then the curve takes you to where you can find the equally distributed equivalent, which is D, less than the mean. This is the fundamental construct of Atkinson's measures, and much of what's done in inequality analysis that's normative. So that's the building block. But then let me just go ahead and look at it another way, because those of you who've had varian, this is another way of looking at it. There's the, utility, okay, and there's the mean. I'm going to have equal weights on x1 and x2. There's the mean, and that's the utility function, and there's utility of x1, utility of x2. And so the mean utility level between the two is given at that point, right? And so, right, so this would correspond to the welfare, right? So if I take the welfare back to the utility function and come down, then this gives me the certainty equivalent, or equally distributed equivalent income. Okay? So that's the structure that and notice it's always going to be less when you have this curvature. There's always the risk premium, if you will. And here's the inequality measure class that they talked about, Atkinson constructed back in 1970. It is the mean minus the equally distributed. You put the welfare function you want in there. This is one way of doing it, measuring inequality as welfare loss. In income space, this is dollars. How many dollars do you lose effectively? Okay. Another way of doing it, if the welfare function satisfies linear homogeneity, then it's not just this, it's saying, well, how much welfare you're losing, because you can measure it all in welfare terms then, because welfare and income are actually measured in the same space. So the lost welfare due to inequality would be another way of interpreting it. Okay. To implement this, though, you need a welfare function. Okay? A little bit of a problem, right? This has been one of my critiques of it because it's not very practical. Of course, you can say that the Gini welfare, the sen welfare makes sense, perhaps. But it's just problematic to try and identify what the welfare function would be. But still, one can put it together. The EDE, by the way, itself is a welfare function. It just satisfies additional properties that make it more useful, linear homogeneity and so on. Atkinson's class of measures built on this structure are as follows. He begins with a welfare function. He then assumes this very well-known class of utility functions, assumes it, and derives the equally distributed equivalent as given here. So you can tell that this is raising each income to a power, averaging, and then undoing that power. So you're measuring back in income space. For this is the geometric mean, multiplying all incomes, dividing, taking the nth root of them. So those are the building blocks of his measures. He only looks at alpha less than 1 because he's interested in measures that satisfy the transfer principle with the formula that we had up before. There's the Atkinson class. It's Lorentz consistent. You have a parameter that measures inequality aversion. This is great for robustness discussions. You can talk about, well, what if alpha was between this and that? You could evaluate this inequality aversion is very similar to risk aversion. Some people identify the two. Each member is a monotonic transformation of a generalized entropy measure. Surprisingly enough, I like this a heck of a lot better. It's subgroup consistent, but it isn't additively decomposable. So it doesn't work as well in certain types of applications, empirical applications, but it has all the nice normative properties that you would want. So there's a summary. Rich array of inequality measures. How do you select between those, or there's some that we haven't even mentioned yet that I should mention. Well, one way is through properties. One way is through interpretation. My favorite way is, of course, other people use it and it's in my statistics package. Right? That's how people choose. Is there an alternative approach? I want to stop for a second. Looks like I've been going for how long? Aha, an hour, great. So let me pause and ask if there's any questions before I proceed to quasi-orderings.
So you're talking about these inequality measures based on income distributions?
Income or
Okay, or
consumption.
So, or consumption. I was thinking about different sort of measures of inequality, like life expectancy or
Yes.
cognitive ability.
Yes.
Is there something specific about the distributions you have to keep in mind in order for?
Number one, if you have an upper limit, things may be different. In other words, if you have a limited range, then the type of inequality measures that are used and that look at income, which does have an upper limit in any year but continues moving up and down. Scale and variance, does it really matter? You can't go beyond this range. So there are issues that have to be attended to that have not been studied. Some people have talked about them sort of inadvertently, but they haven't really been studied theoretically. There may be good reason, and I have a student who wrote a paper this term in my class, may be good reason to use these sorts of absolute measures when you have a limited range. Okay, so he was looking at growth rates and the variance or the difference in growth rates across countries and trying to make sense of whether that's changed over time. Well, with growth rates, there's a pretty limited range of things. And so he thought it also makes better sense to look at absolute measures. So that you subtract 1% from every country, it's more or less the same inequality. Some become negative, therefore negative values, you can't deal with most of these measures when you have negative values. Some you can, but with absolute measures, it's just a translation, so it's fine. So there are issues that are in the data, that are of the data. Wealth, I would expect, has to be measured differently than income because you have so many negative entries and you have all kinds of different situations in that case. So agreed, this is primarily for the kind of archetypical income consumption, and it can go to other variables, but you have to be careful and reflect on it. Yes, other questions? I'm sorry, you're out. Yeah, you said the last one, unless you want to lie. Sorry, no question? Oh, okay, you're going to give him your, go ahead.
I wanted to ask, and this goes to Jim's opening lecture, where he talked about, well, let's go to Steve's lecture too, where we're talking about there's a lot of focus that's been done on measuring inequality across sections.
Yep.
I wanted to know if you can talk about, are these measures particularly strong in terms of measuring cross-sectional inequality?
Yeah, they're only for cross-section, but they are the basis of many of the mobility measures, and poverty measures are the basis of many of the mobility measures. So there's some, the mobility measures, I have a new paper coming out on, which has a particular approach to mobility, which looks at movements across a cutoff, one cutoff, up, down. Look at the head counts, the percentage. and then let the cutoff vary. So it's a dominance approach. Yeah, go ahead, sorry.
I was thinking more in the space of like understanding inequality within a specific country, like across time. So like looking at like.
You need non-anonymous data. You need data that allows you to see in period 1 and period 2 the same person. Once you have that, then you can formulate measures that are quite similar to what we're talking about in income inequality, but they take into account the fact that you can link across periods.
And a related question is like, have there been inequality measures that kind of like look at, say for example, tax burden? Because oftentimes like these questions center around.
You can apply it to tax burden if you wish.
Yeah, like that.
But it then becomes kind of multidimensional because you have the taxes paid plus initial income. So you have two things you're interested in, let's say.
Yeah, because I mean, like in a sense, like what wealthy people may argue is that they are disproportionately paying a higher share of the tax burden, and that is increasing over time, right? And so from their standpoint, like if we were to measure inequality based on that, then they might say in the U.S. like inequality is increasing, like from a measure like that. So, and at the end of the day, like I think we are very concerned about redistribution. So it seems like finding some way to bring in.
The Lorenz curve has been used extensively to measure progressivity of taxes in practice and in principle. In fact, it was found in Brazil that all of these fancy taxes and fiscal policies do in fact hurt a lot of people at the lower end. And this was Nora Lustig, a paper very recently. It should be all over the web, Lustig. And in her case, she was finding that pretty reasonable proportions, some 10%, 20% at the low end, were being socked, especially by the food taxes, which you would expect. And the fiscal stuff didn't help them at the end of the day enough to recover from their loss from the original tax. This was quite interesting. So all of this can be done with this technology. It's a matter of adapting it, and that's why I'm presenting this first to talk about it later. Yes. Other questions? Yes.
You mentioned that if one Lorenz curve dominates the other one,
yep.
You can move from one to the other by transfer.
That's right. For discrete distributions, it's straightforward. For non-discrete distributions, it's Rothschild-Stiglitz, the same proof that they present in their increasing risk paper.
No, but actually I don't understand why you build dominance condition. Why is that not true always? That you can go figure out the same number of people.
It's transfers of the same direction. Progressive, 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 progressive. Of course, you can always do transfers.
You improve every time.
That's it. So the Lorenz is kind of a cumulative improvement, if you will, in terms of progressive transfer. Okay. All right, so let's elaborate a little bit more on this notion of the Lorenz comparisons or unambiguous comparisons or unanimous comparisons of inequality. What would unanimous mean? It would mean all of the indices that we might imagine all agree that things have gotten better, whatever better means. Okay? Unambiguous would be, well, by this criterion that we really believe in, the income distribution has changed according to that criterion. So we know unambiguously that we are at a better position. Does anyone know any quasi-orderings, by the way? Quasi-orderings like Pareto dominance is a quasi-ordering. There's lots of quasi-orderings we use frequently in economics. I'll talk about a few of them right now, okay, in inequality analysis. Inequality measures generate an ordering of distributions, right? You can always rank any two distributions once you measure them with the Gini. Other criteria, such as Lorenz, are quasi-orderings. They're transitive, they're reflexive, but they're not complete. Okay? Quasi-orderings don't compare all distributions, but it reflects the complexity of decisions. So it makes sense. Perhaps we can only make these decisions and not the others. So it really is dealing with kind of an ambiguity or a conflicting principles behind what you're trying to measure. There's two forms of quasi-orderings that I mentioned before, unambiguous, unanimous. For instance, here's intersection ordering or unanimous quasi-ordering. Take three indices. I don't care, Gini, one of the Atkinsons, a generalized entropy, and say that we'll only agree that inequality is increased if they are consistent. This is a robustness analysis, right? That quasi-ordering so created, right? It's transitive, right? It's reflexive. Okay, so that's the underlying structure of quasi-orderings in inequality world. Let me give you an idea of what the Combe triangle is, because it's such a useful thing for depicting distributions, in this case among three people. Serge Combe, who's a French economist, who's done tons of work in this area, okay, including a paper that was very similar to Tony Atkinson's 1970 paper in '68. So let's say we have three persons, we have a total amount of income T. How do we represent that? Well, how about that way? Barycentric coordinates from years ago. Okay, so this is just up on top. The person 1 has everything over here to this side. Person 3 has everything over there. Person 2 has everything. And you can represent everything as a convex combination of those three. So in the middle, equal. All right. There it is. For any x, the coordinate xi is the distance to the ith edge. So there you measure it for the equality with the mean, right? For that one, it's x2, there's x3, and the vertical is x1. All right. So this is the iso inequality set for the coefficient of variation. Nice circle. You'd expect that, right? There's for the second-tile measure. It's more extended. It's reflecting a bit more sensitivity to the poorest, and not caring so much about the rich guys. Tile measure is in between those two cases. Now, where do they all agree? They all will agree that there's less inequality as you go in the middle of them, right? Just take the lowest or the one closest to the middle, and that would define a range where they all agree. Where do they all say that you have higher level of inequality? Outside of all of them. So in this area that kind of flares down and goes across, the outside area. So we're describing something which could be taken to a limit. If we took it to a limit, we'd probably get something which looks like that. This is the Lorenz dominating area. For this distribution, or for the x up here, wherever it is, it's gone away, everything inside that hexagon, Lorenz dominates the distribution. And that's a pictorial representation of it. You can actually see it because it's a series of inequalities, and the inequalities bind at the edge. And then those that have unambiguously more inequality, according to the Lorenz criterion, are those in this gray area, right? Because the poorest here has got less. Okay, so that's going to cut things down. And these are the two regions defined by Lorenz. The other white regions, you can't compare. That's the crossing. All right. When do all relative inequality measures agree? Clearly, when the distributions can be compared by the Lorenz criterion. So that's what this theorem essentially says. So unambiguous comparisons can be made if and only if unanimous comparisons can be made by this class of measures. Quite nice, isn't it? Additional property of transfer sensitivity buys you more. And I gave you the idea of a transfer that had a kind of progressive transfer at the low end, a regressive transfer at the high end. They're kind of the same magnitude. Call that a fact. If you have a fact, then you should, under transfer-sensitive inequality measures, have lower inequality after the fact. I'm not going to give you this example, but you can just believe me, it works. When do all inequality measures satisfying transfer sensitivity agree? Well, third-order dominance. And I'll tell you about stochastic dominance in just a second. But there's the picture of third-order dominance in 2 seconds. Give it to me, give it to me. Yes. So with third-order dominance, you get this little edge right here, and here, and here, and here, and here, additional, that you can compare and say is worse. And you get this little area here, here, and here, which is less unequal, more equal. So you augment the set of potential comparable points by having fewer inequality measures with a property that emphasizes the inequality among the poor. This is the idea. All right. welfare quasi-orderings, and I'm mentioning welfare quasi-orderings because this is the way the literature went, not inequality quasi-orderings. It all started with Atkinson talking about things that we now have come to know are just pure and simple stochastic dominants. I want to mention this to you because it's so important for both poverty, inequality, and all distributional analysis. Suppose we know the general form of a welfare function. It's utilitarian with some u as the individual utility. So it has u prime greater than 0, u double prime less than 0. We don't know the specific form of u. Can anything be said about welfare? If we have two distributions, because remember, these utility functions are indirect utility. They're on income, holding prices fixed. Okay? And we're assuming they're the same across people. Can we say something about welfare? So given two income distributions, x and y, when does one have higher welfare for all such welfare functions? This is another unanimity quasi-ordering, where all people in this room would agree. If you had a welfare function over all of us and you thought, oh, here's the welfare function I would apply and here's the one I would apply. But they're all in the right class, this particular one defined above. When would we all agree? Well, utilitarian welfare is really identical to expected utility in form. So let's draw from the risk literature. Here's the discrete case. Expected utility is just average utility. Continuous case, this integral. X is now viewed as a lottery, or f of s could be the lottery as well. To choose between risky lotteries without knowing the specific utility function, now it's your utility function choosing between two lotteries. It turns out that we have a lot of things available to us. One distribution is said to stochastically dominate another if it yields higher expected utility for all utility functions in whatever the class that you have defined a priori. The one we did a second ago was u prime greater than 0, u double prime less than 0. Okay? That's a general definition of stochastic dominance relative to the class U. Now there are specific classes that we use frequently. One, I like money. U prime greater than 0, it isn't equivalent, but it gives you the same ordering as if you had an increasing function. It's just u prime greater than 0 doesn't imply, I mean, that's not all increasing functions. It could be non-differentiable, right? Okay. Second is the case we just talked about, and it yields, the first yields first-order stochastic dominance, the second yields second-order stochastic dominance, and the third has convex marginal utility. What the heck does convex marginal utility mean? Does anyone know? Give me some idea. Any risk folks out there? What does marginal utility look like in this world? Downward sloping. Okay? So what's happening is that it's downward sloping and becoming flatter. So the difference between people the same income distance apart is getting less. Transfer at the lower end is going to have a bigger effect than a transfer at the upper end. Ah, okay, that's what it means. So here's the theorem by Bawa on stochastic dominance. It says to figure out whether two distributions can be compared for all those utility functions, it's easy. In the first case, just look at the CDFs. The one with the higher CDF, giving more weight to lower incomes, is worse. The second case, you take an integral of the first of the CDF. Take a look at the integral functions. Compare those two. If one of them is above the other, it's worse. Do it again, one more time, integrating for third-order stochastic dominance. Plus, you have to add a little funny business about the mean, but don't worry about it. And that's the criterion for third-order stochastic dominance. This result is well known, well understood, and really interesting. So first-order stochastic dominance looks like this. F better than G. What about the quantile functions? Yeah, flip it. F is higher. Yeah, that makes sense. Second-order stochastic dominance. Here's a typical picture you'll see. They don't have to be common mean. First-order dominance implies second-order dominance. Because if everyone with, positive marginal utility agrees on something, then the subset that happens to have diminishing marginal utility will also agree. So second-order dominance is implied by first. But we do it for this case. Let's suppose the area between them is the same above as below. Then the integral is such that the integral of G is always as high or higher than the integral for f, the integral function, and you get second order stochastic dominance according to Balois. What about qf and qg? Again, it's the integral as well, but what's interesting about it, because the area one way and the area the other way have to correspond, it's not the same area, but the ordering has to be the same. This area we knew before as being related to the Lorenz curve. We integrated the quantile to get the Lorenz curve and divided by the mean. So that's what's going on here. We'll relate welfare to Lorenz almost directly for common mean comparisons. Atkinson's theorem is just that. It says, look, if you have two distributions with the same mean, the following are equivalent. F Lorenz dominates G. The welfare of F is as high or higher, that is, in G. For all utilitarian social welfare functions with U prime greater than 0, U double prime less than 0. And F, second order stochastic dominance G. This is really interesting, and it was an amazing breakthrough because we had no idea that inequality could be so tightly linked to welfare. Note the tightness is not that tight because we're assuming identical utilities. We're assuming all kinds of other stuff with this class of welfare functions. But nonetheless, okay, we use this class frequently for a lot of things. The proof is just the graphs. Integrate the quantile. If you have the same mean, that function is higher, then the function with the mean would be higher, hence the Lorenz would be higher. No need to even prove it, it's just a graph.
This is when all the gray alerts are for.
When all the, what is?
Welfare functions are gray alerts.
Yes, so we have the same, in other words, we have identical weights on every person, and the utility function, the weight, the way that we map income to our indicator of welfare is the same. Sen, of course, would argue this is preposterous at the end of the day because the utility functions are different for all people, hence we have to get out of utility space anyway. We can't make any calculations. Let's go to capability space where things actually can be compared. Yes?
I guess to put the engaged sense on it a bit more.
Okay.
Like, could you argue that we care about this from the point of view of the social planner, means that the social planner like, has a utility function that the social planner can choose what utility they assign to different people.
They certainly do in lots of papers I've read.
Yeah, so from that sense, like that criticism, like, does it have any kind of interest?
Well, that's interesting because if the planner restricts themselves to this class, then no matter what is chosen, in this case, everyone would agree. All the planners in the room would agree that what's better. That's what this theorem is saying. But in practicality, I think it's very impractical to talk about converting to utility functions for the purposes of actual analysis of policy on a regular basis, because it's hard to defend one particular utility function or the other. You need classes almost.
I guess like, from a practical standpoint, there are 5 people in Congress who are choosing how to distribute resources. So from their standpoint, like, they have a certain universe, like, if they sat down and like, talk, and need to figure out like, what are the principles that they act on, like any utility function that match.
You might be able to. Any comments on being able to infer revealed preference from members of Congress? I live in DC. Not so sure. Yeah.
So this theorem is meant to compare welfare over time, or what's going to be the use?
It's actually a static sort of measure of welfare, but it could be the same country at 2 periods of time. It could be this 2 different countries.
Then I think the more interesting question, at least to me, would
Yes.
be what is the trade-off between inequality and mean?
Exactly. In fact, that is the typical question from public finance. What's the trade-off between equality and mean? And the Atkinson measures make that trade-off in terms of the equally distributed equivalent. That's a welfare function. And it's making that trade-off explicit. But how do you make that trade-off explicit? How do you fix a particular welfare function? It's too hard. So you have to think of ranges, perhaps, of welfare functions. But you're right, it is the main question.
So here you assume that both means are the same, right?
Mm-hmm. Yes. By the way, just to let you know, that the 2 means are the same is irrelevant. Doesn't matter. Don't use the Lorenz curve. Use the generalized Lorenz curve. The integral function underneath the quantile function. It's called the generalized Lorenz. It maps up here to the mean. It looks like this. If you compare using generalized Lorenz, one is higher. Unambiguously for all welfare functions, it will have higher welfare. The mean case is actually a red herring. And Tony Shorrocks is the one who proved that particular theorem. Yes?
I'm really confused this time. So what is, can you say what is, I mean, if you want to prescribe something to economy and you see the economy is growing with 12% a year, at the same time, you know, it's probably not that, it's not clear if they're progressing with respect to the measures of inequality. How are we going to trade off between this steep growth and inequality? Would that be better for some time that, you know, to let the economy grow at 12%, and then, you know, to think about inequality? So this trade-off between growth and inequality, I don't see how, you know, coming in this measure.
The trade-off between growth and inequality.
Or is there a trade-off? I mean, I think this is the most interesting thing. I mean, to me, how are we gonna? I don't know if I make my point clear, but.
So what is growth? Growth is a change in means.
That's right. And here we're assuming you know, the same means. So if you look over time and you say I can compare inequality only if the country, you know, the GDP per capita stays the same.
Don't worry, you can go beyond, and that's what's done next. Okay, so you do go beyond the fact that you're holding in mean fixed here. If the mean rises fast enough, even if there's more inequality, the generalized Lorenz will be higher and welfare will be unambiguously higher. That's the idea with these unambiguous quasi-orderings. Of course, if it's not high enough, then you still have to worry about the trade-off. And that's the big trade-off between the two. But sometimes you don't have to worry about the trade-off, that in fact the mean growth is high enough to propel people up high enough so that the second-order dominance result says that welfare is higher. Do you see that? If you don't, I'll try and show it to you in just 1 second, because there's a result that will arise. Okay. So the first extension was to welfare functions that weren't utilitarian. So Sen's welfare function is one that's not utilitarian. It's a very strange one. It's behind the genie. He generalized Atkinson in one direction because he actually has a bigger class of welfare functions. In the other direction, it's a worse result. It's not as strong a result. I used to think this was trivial, but now knowing that the Sen welfare function is there and makes sense, and it's been expanded. This class is now used a heck of a lot in decision theory. So those of you who've studied decision theory, these non-additive utility functions, this is the same structure behind the genie. Shorrock extended the theorem to the case of different means by using the generalized Lorenz. And in fact, it's just the integral of the quantile function. Higher integral of quantile, you're done. It can be that you have actually lowered for some people, but if it's made up by the lower income people, that's the trade-off that's going on here. And there's, again, no need to look at the trade-off between mean and inequality because you're getting dominance for all the welfare functions. If you don't, then of course we'll have to go back and worry about more explicitly the trade-off and finding the narrower class of welfare functions for which you might have an increase, a decrease, or just say, we don't know. So there's the generalized Lorenz curve. I just integrated the quantile. You can easily see what's happening. I won't burden you with that. So here's the theorem. If F generalized Lorenz dominates G, take the integral of the quantile. If it's higher, then F generalized Lorenz dominates G. Welfare is higher for all of these classes of welfare functions, and F second order stochastic dominates G. The proof is just graphs. Flip, integrate, use the Bawa first integral condition where you integrate the CDFs. It's the same thing as integrating the quantiles. Okay, extension to transfer sensitivity. Which is higher welfare, this or that? Under U3 with U triple prime greater than 0, X has higher welfare than X prime. Again, it's one of those facts, right? You can see the transfer going on that's actually hurting the lower people and helping the higher people in the sense of inequality. So you know that it's going to be higher. Ooh, which way will it go? I think that that's the other way around, isn't it? So X has got equal, yes, oh yes. So in going from X prime to X is a fact, and therefore X is the higher welfare than X prime. The means are the same. All transfer sensitive inequality measures would also say that you have less inequality with X, in addition to having higher welfare. So SD3 is that transfer sensitive inequality measure, quasi-ordering, but it broadens it to cases where the means can change. Subgroup properties and characterizations. And I have just a short time left in this. Let me just double check. Yeah, about 20 minutes. So subgroup properties help to answer questions like, in most of global inequality, is most of inequality within country or between country? How much of total inequality in wages is due to gender inequality? How much of today's inequality is due to purely demographic factors? The source of all this is the analysis of variance. That's what all the decompositions simply are. So as you look through the complicated formula, just realize you know it already. And it's just a variation of a theme. Example. I don't want to talk about this example. Yeah, what makes everything possible is decomposition of variance. You know that. Okay, so additive decomposability looks like this. It says inequality of an entire population, north and south, X and Y, can be decomposed, weighting the inequality within X, adding it to weighted inequality within Y, and adding it to the between group term, which smoothed out the inequality within group and left only inequality between groups. So it's usually stated for any number of groups. I just have it for 2 here because it's a lot easier to state. This is the between group contribution. The explained inequality is the amount due to gender inequality, for instance, if it was men, women. And this is the within group contribution, could be called unexplained inequality. Tile's entropy measure has this decomposition. Tile's second measure has the population share weighted. Tile's has the income share weighted, so the richer groups have more say as to how inequality is determined. Squared coefficient of variation has a strange weighting that we talked about before. And generalized entropy measures have this general weighting structure. It's the ratio first of the population sizes and then the ratio of the means. So that's group mean over total mean, group population size over total population size, and there's some power alpha on the income side. And that alpha, of course, goes negative and positive. So you can see for some measures, it means that you have a higher weight on income, and other measures, it's actually pulling back if you have higher income. I'm not going to go through these examples. You can do it at your leisure as to what happens when you change things. But essentially, the tile measure is only the ones with the weighting summing to 1. Between group term is smaller. It fell slightly. Let's not worry about that. The Gini breakdown is what I'm really interested in showing to you because it has a strange form, and it's both a positive and a negative in calculating inequality. Could there be weights so the Gini measure actually breaks up nicely? And the answer is no. In this case, where you have 2 sets, one of the groups has all incomes below all the other incomes of the other. So we have 10, 12, 12 versus 15, 21, 32. Everything works great with the Gini. It has a decomposition with the weights that I gave you before. It's beautiful. You have the populations here, the means here, inequality levels I've calculated. The weights are given here and here by that formula I mentioned before. Within group term is given here. Between group term is given here. Everything adds up. Add up the within group, between group, you get the total. There's no residual because you have non-overlapping groups. But as soon as the groups become overlapping, the sum of the within and between is not the same. It's less than the overall Gini. And why is that? It's because the Gini has this really interesting property of when you have overlapping, you're having more inequality because of the distance between the 2 people. The impact of having a greater spread between 2 people depends on the number of people between the 2. And so as you put people from another group in between 2 people, it affects their contribution to the measure. And it's a way you can't recover from individual data. You just have to call it a residual. And that's what's done in the literature. Now this is all between population. There's other forms of decomposition we'll talk about after a while, but this is between population, you get this residual. So it uses rank order. This is very easy to see if you use the definition I gave you of this expected difference. You get a matrix, and you'll actually be able to cut the matrix into 4 sections. One part is within one group, one part is within another group. The other corresponds to between, and if they don't overlap, it stays between, but if they do overlap, these are not between anymore and you have to create a residual. That's the idea. You can do the exercise yourself. It's very straightforward. Yes, please.
So does the tile, I thought that the tile also had to have non-overlapping.
No, it doesn't. It works with everything on Earth. So the decompositions of the generalized entropy are of the general form. They're not just a breakdown, which is what we have here with the Gini. So what inequality measure is decomposable? Well, I just wanted to express in this context the way that a lot of us do business. We start with axioms. We then work through the axioms mathematically, derive what's possible, and then present it back in the form of a class of measures. It's really cool stuff. So for all the theorists in the room, I thought I'd take a second to talk about the methodology of this stuff. So you start with a generic I function. You assume that I satisfies some properties. And you show that they actually impose certain mathematical restrictions on some function, say f, related to the inequality measure. Then you use this f to reconstruct the I, and therefore it tells you what inequality measure can be done. This is how so many papers in inequality and lots of measurement literature do the job. Okay, what form of math is used? I'm going to mention the form of math because it's quite neat. It's functional equations. You know differential equations. That's something you're happy with. Well, maybe not. But in any case, what you're doing is you're saying, here's a function that involves taking derivative of something here and there. And then the only f that satisfies this expression we start with is this function. Cool. So we place restrictions on the function through the form of equations that must be satisfied involving different. Well, here you don't have any derivatives being taken. So look on the left here. You have the Cauchy equations. There are 4 equations that are well defined in mathematics. F of a plus b is equal to f of a plus f of b. Well, under very simple conditions, you can show that f has to be linear. The second one, it has to be exponential. The third one has to be log. The final one, it has to be power. So we use those sorts of things, those solutions that have been done by others, a guy named Axel, to find the solutions to equations satisfying either continuity or some sort of regularity condition, and then the properties under consideration. So we assume that I satisfies the various axioms. We derive this function, blah, 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 blah. Okay. So suppose we like Theil's form of decomposition. So there it is. Okay. Is there any other relative measure that has this decomposition? And the answer is, well, I is Lorentz consistent and satisfies that. It means that it's Theil's up to a positive. So how does that happen? How do you prove that sort of thing? That Theil is the only one that satisfies it. It seems very complicated to do. It actually isn't all that complicated. The key step is you set f of s to be equal to I of s, 1 minus s, where s is something between 0 and 1. That's the function that I define, that I need to construct to work my mathematical stuff on. Note that f of s is equal to f of 1 minus s by symmetry, by Theil decomposability and Lorentz consistency. It turns out that this holds. But this is an equation, a functional equation that's well known in the literature. And it gives me a solution. And the solution is f is equal to t log t plus 1 minus t log 1 minus t. That's a solution. That is building up to the form that you saw with the Theil measure, with the logs. It was income share times log of income share. So it eventually gives you t back. So that's the structure of axiomatic characterizations in this literature. The initial papers were by Bourguignon and Shorrock. They characterized the Theil measures and so on, but used differentiability, which, here's the Gini coefficient ISO inequality sets. Notice they're not differentiable. They have points. So it didn't apply even to Gini. So they had to generalize to continuity. It was done. And assumed continuity, assumed additive decomposability. And he showed that, in fact, the theorem was as follows, the kind of general theorem. If you have continuous normalized Lorentz consistent inequality measure satisfying this additive decomposability, then it has to be a generalized entropy measure. We're stuck with that horrific form if we want to have a decomposition. He actually proved a more general result, And let me explain that more general result because it's more interesting to me. It's as follows. So, subgroup consistency we've already talked about. It was actually coming out of a paper by Frank Cowell years ago that no one's read, talking about 3 bad measures, which included Gini and a few others. Subgroup consistency, if inequality rises in one subgroup and another, hold mean population fixed, then it should rise over all. Note, if I is additively decomposable, then it's subgroup consistent. We know that because the inequality within terms always will rise, therefore raising everything. So all generalized entropy measures are subgroup consistent because they're additively decomposable. The same is true for increasing transformations of the generalized entropy, which includes the Atkinson group. But here's the theorem by Shorrock, which sort of brings everything down to a basic level. But there's a generalization of this that needs to be done, and I haven't done it, and I'll do it after the second lecture. I is Lorentz consistent, continuous, normalized inequality measure satisfying subgroup consistency, if and only if it's a function of the generalized Lorentz, the generalized entropy measures, I mean. So this is saying, look, if you're going to have subgroup consistency, if you're going to require this consistency, then it has to be this class of measures among all relative measures. Now my question is, suppose you don't require relative measures. 90-10 is fine. You don't satisfy transfer sensitivity. Is there a theorem out there that could characterize the 1% type measures that have this type of property? I haven't done that yet. I'm interested in that. But I first have to create the theory that unifies inequality measurement that's done in the next lecture. Okay, the Gini violates this, and I won't get into the example, but it's true. Here's the discussion of all this. Decomposability is useful. It's not always needed. It represents a pretty strong restriction, but it can be generalized. Subgroup consistency is pretty compelling. But Sen completely disagrees with it, and we have arguments. When I was teaching at Harvard a few years back, we had arguments in class about this. He won the argument in class. I had the next lecture, so I came back and told what he was doing wrong, which was he was assuming that symmetry didn't hold. But inequality, on the other hand, is quite relative, so I'm not sure. Maybe the Gini is capturing something more. So maybe subgroup consistency isn't that perfect. That's what Sen would say. And an example is given in the book. But summary, I just given you some key elements of inequality measurement as the theory people would want you to have. This is what people take as the bulk of the basic theory as given in Sen's book with me. You have an array of inequality measures. 4 basic properties help to discern, at least to some extent, a kind of coherent framework for measuring inequality. Subgroup properties are used to characterize measures. They're very helpful in doing so. What's missing? Well, I haven't talked about decomposition by source. In fact, Shorrock's paper does discuss this, and it turns out I still don't have a good sense as to the generality of the result, but he kind of comes back to a variance result and says, well, we have to use the variance decomposition. Shift-share analysis, I did not talk about at all. Shift-share analysis, or saying, well, let's suppose we have a change in 2 periods of time. Demographic shifts occur at the same time. We can use the decomposition and the weights on the decomposition to look at a counterfactual. Suppose we had the same demographic factors today as we had last time. What would have happened to inequality? And that's done by a number of people, DiNardo, Chico Ferreira at the World Bank, Francois Bourguignon, lots and lots, and Bob Margo did it in an early paper, Dilip Mukherjee and Tony Shorrock did it in an early paper as well. Very interesting analysis, and that's where a lot of the fun comes in. Mobility, non-anonymous comparisons. Take all I've said, if you have a panel, you now can do more. Or retrospective, you know what people had last night, okay. You can do more. And what they've been doing, and what we've been doing at the World Bank, because there's been a lot of interest in mobility at the bank, is to realize that it's just what static measures do. They look at things anonymously over time. We don't connect the 2 periods. We just say, okay, you were here, you're here, but we're not paying attention that you moved. We're just going to look at the distribution change irrespective of who it was. But mobility approaches have to be non-anonymous and based on where you were. So it might be quite nice to take the quantile function and see where people went after that. So how much growth was there in different parts of the quantile. But taking into account the person who's there, not just the quantile. You get a raggedy-edged picture. But it's quite interesting, and by actually looking at small sets, you can get a sense as to sort of the changes that have occurred. So they've had a very interesting flagship publication recently on mobility at the bank that would be quite an interesting thing to read, but I'm just not going to focus on mobility here, I'm afraid. But you can look online, they'll have it. Look under Francisco Ferreira. Also, Luis Felipe Lopez Calva has done some very interesting work on the middle class and mobility in the same group. Okay, that's it for right now. Thank you. I'm done for this 2 hours. Yes?
There's a lot of work on mobility.
Absolutely.
Various ways to focus on those. I mean,
The reason why I don't focus on mobility is that, to be honest, there's no theory yet that can link together the different measures of mobility. They're also very disparate and hard to explain in relationship with one another. And I'm a theorist. I want to have it fit. And until I can make it fit, I'm going to say, well, maybe I'll make contributions myself, but as far as lecturing on it at this point, I'm less happy with the results. But I'd be happy to talk about it after a while.
I'm just curious, we have a whole theory of income processes, employment processes, that gives you a natural dynamic, and that gives you natural measures of mobility. You take the individual, you follow the individual earnings over time, you can compute a bunch of mobility measures also.
Yes, and there's 20 different measures that one can compute if you look at the survey of Gary Fields. Yes, but why one versus the other? It still isn't the guidance at all of any basic principles that seem to be pushing
If you're
people.
going to go introduce
Yep.
utility, you can then say, okay, now we've got life cycle utility. We have life cycle, we have utility function over life cycle of realization. Plus, maybe some credit constraints, some margins, and so forth. And then we place some welfare judgments on lifetime utilities.
Have no problem.
Defined recursive. That would be-
I've written a paper on chronic poverty, which is just that.
Right.
It's essentially looking at welfare cutoffs and saying, here's a person who's, on average, their welfare is below the cutoff. That person's considered poor, and we focus on that group of people who are chronically poor in terms of permanent income, if you will. That's the persons that we look at and we measure, and we look at the inequality among that group. And so, yes, it could be extended, again, to the entire
I'm just thinking,
group of
I think
people.
the orderings on lifetime. So I just aggregate or integrate up utilities over all the life of the individual. Maybe you find a recursive and given the available information we got had.
How good is your model?
Well, no, but the model is basically one of the standard life cycle model. I think that's a good work. I'm surprised you just don't see that as a natural edge.
It's natural, it's just not there yet, in my opinion. So when I focus on it, when I focus on the underlying principles that might guide our way of looking at that, I'll be into it. And I'm just starting doing that. My focus has shifted a little bit to mobility recently with a student of mine. And so that might happen in the next few years. But there's limited gray matter, I'm afraid.